तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
So, the last two classes we were discussing the p-n junction diode, and now we move on to the next more device in terms of complication, okay, BJT, the bipolar junction transistor. Okay. The model which we shall discuss for the bipolar junction transistor is the Ebers-Moll model, which is a simple yet a very useful model, okay, and it can be applied in most cases, and we shall be applying it also in our discussion on integrated circuits as such. So, the Ebers-Moll model of the bipolar junction transistor considers the bipolar junction transistor, which you know is a 3-terminal device consisting of 2 p-n junctions, as 2 diodes connected back to back. Okay. So, you have, if you have an n-p-n transistor, you have one p-n junction and the other p-n junction like this. Okay. In addition, you have 2 current sources okay. These current sources gives us the coupling between the 2 junctions. Okay. So, if you, this is the emitter terminal, say this is the collector terminal, and if this is the base terminal, if we call this current IF, okay, which is the forward current, okay, and is given by IES, which is the same diode relation which we are writing down now. I think I should write it down here. IF equal and you have the other current IR. Okay. So, this is the base collector junction. So, this depends on the base collector voltage. IR is equal to, you know, the constant okay, and these current sources are actually the coupling between the 2 junctions. So, this is given by a constant into IF, okay. The constant is called alpha F, and this current source is given by alpha R IR, okay, where alpha R is another constant. So, the idea of this model is that if you know the applied voltages between the junctions, for example, here you have 2 voltages, emitter base and base collector, you should be able to evaluate the different terminal currents, that is the emitter current, which in a normal NPN transistor will be flowing in this way, IE. You have the collector current, okay, which flows this way, and you have the base current which flows this way. So, we should be able to evaluate the 3 terminal currents in terms of the 2 voltages, okay, that is the emitter base and the base collector voltages. In order to do that, now we see that we have 4 constants which are to be or 4 parameters which have to be known beforehand, that is IES, ICS, alpha f and alpha r. Okay. If you know these parameters, you will be able to evaluate the terminal currents. So, now let us see what these parameters depend on, etc. Okay. We shall go ahead in developing this model. Okay. All right. Now, just before we go ahead, if we take for example, VBC is equal to 0, okay, in this transistor, what does it imply? IR is equal to 0. If VBC is equal to 0, IR is equal to 0. Okay. Then what do we have? We have IC is equal to, what is it? Alpha f IF, because this current is 0. IE is equal to okay, this IR is equal to 0. So, this current source is 0. So, and IB is equal to 1 minus alpha f IF, okay, which gives us that if you take the ratio of the collector current to the emitter current, it is equal to IF is equal to alpha f, which is called the common base current gain. Okay. And if you take the ratio of the base current to the collector current, you have this is equal to IC by IB will be equal to alpha f by 1 minus alpha f. Okay. So, I shall write it here, IC by IB is equal to alpha f by 1 minus alpha f, which is equal to, it's called beta f, which is called the forward current gain. So, in this condition, when IR is equal to 0 or VBC is equal to 0, all these terms we are in the forward mode of operation, okay, and we have the beta f or the common emitter current gain as the ratio of collector current to the base current. Okay. You can also have the reverse mode of operation, in which case in reverse mode, if VB is equal to 0, you have IF is equal to 0, okay, and you will have similarly all IF, if you put as equal to 0, okay, you will have, you are operating on the reverse direction. So, IE by IB will be equal to so this is called the reverse beta of the transistor. Okay. So, you can have the forward mode of conduction and the reverse mode, and if you consider that both the forward and the reverse current exist, so the normal mode, that is VBE is not equal to 0, VBC is not equal to 0, IC is equal to what is IC equal to? Alpha f IF minus IR. What is IE equal to? Okay, this is IF minus alpha r IR, and IB will of course be equal to Ix plus. So, these are the different currents, okay, as given by this model, all right. Now, what we shall do is we shall consider the different, try to evaluate these currents and try to get a simplified model. Basically, what is done is we shall be able to see that instead of 4 parameters which we now have, okay, we shall be able to eliminate one of them, okay, and write the equations in terms of 3 parameters. Okay. To do that, now let us again take the transistor. So, this is the emitter, this is the base, say, and this is the collector. All right. Now, suppose you have, this is NPN transistor. Okay. So, suppose we have forward bias this emitter base junction. Okay. Now, let us look at the charge profiles in the device. Okay. Now, if you have forward bias this junction, so this is the depletion region. How will the charge profile look like? This is the excess charge profile. Okay. So, I draw it like this. Okay. We have already seen for a diode, okay, if you have a forward bias diode, how the excess charge profile looks like. It is basically the same thing. Okay. Only thing we have considered the profile to be of a short base diode. Okay, that is, the profile changes linearly, which is true in all modern day devices, because the actual size of the device, you know, in all modern day integrated circuits would be much less than 10 microns. Okay, even much less in some cases, whereas the diffusion lengths, okay, is lengths are much larger. Okay. So, we can always assume that these profiles are linear. All right. So, this is the charge profile if you forward bias the emitter base junction, and this is the emitter base voltage VBE. And then suppose this base collector junction is also forward biased, then what happens? Okay, you will have a similar situation. All right, you will have draw this like this. Okay. So, these charges, okay, this charge, okay, let me call this QE, okay, this is QBF, okay. The F actually stands for the forward case, okay, that is when you have the emitter base junction applied voltage. All right. We have seen that you have two cases when you have the emitter base voltage applied and the base collector is 0, we call that the forward case, okay, forward mode of operation. And the reverse mode, okay, when you have these charges, well, this is QC, that is the collector charge, and this part, this component, this is the base charge in the reverse direction. So, you have the base charge for the forward case given by this, reverse case like this. Okay. Now, if VBC is equal to 0, all right, then this reverse charge in the base will not be existing, you just have the forward component. Okay. And also if VBC is negative, that is the base collector is reverse biased, this also would not be existing, okay, because you know that the charge at this end is equal to the minority carrier concentration thermal equilibrium value into exponential VBC by VT. If VBC is negative, this is going to be actually negative, okay, and so this is not going to be existing. So if you have both the cases, all right, that is both the junctions are forward biased, the total charge will be the sum of these two charges, and basically you have a charge something like this. Okay. All right. So, okay. Now, if you take just let us take the first case, that is VBE not equal to 0, VBC is equal to 0. Okay. We can write IC is equal to what is IC equal to? It is the current which is flowing here. Okay. So, we can write that is the electron current, this is a diffusion current, okay, and is given by the slope of this. This is almost a straight line, which implies that there is very little recombination in the base. Okay. So, this is the equation for a diffusion current, okay, and this is the slope of the electron concentration in the base. Okay. So, what is dN dx here? It is the slope. Okay. So, it is this height divided by this, okay, the base width, all right. What is this height equal to? Yeah. So, this height is equal to, I can write Ni squared by Na exponential VBE by VT minus 1, okay, divided by the base width. Okay. So, let me write okay. So, this is the collector current, okay, which I can write as IS where IS is equal to Q dN Ni squared by Na okay. All right. Now, I shall go ahead. Okay. So, this is the collector current. Now, what is the base current? Okay, just I will just write here. So, this is equal to, what is this equal to? This is in this model, what is the collector current equal to when VBC is equal to 0, this is equal to alpha f IF. Okay. What is IB equal to? The IB the base current in a bipolar transistor here, okay, in this case would consist of two components, all right, when VBC is equal to 0, all right. What are the two components? One is the whole current which is injected from the base into the emitter, okay, and the other is due to the recombination in the base. Okay. So, holes are flowing into the emitter, so it has to be flowing in from this base terminal, as also there is recombination, okay. That is electrons which flow from the emitter to the collector, part of it gets recombined, okay, and it recombines with holes. So, to compensate for that also holes must flow in. So, basically the base current consists of two components, okay. Now, what is the current which flows into the emitter? Q dP, okay, that is alright, this is in the emitter dP dx, alright, plus I should say Q okay in the base, alright, that is the charge divided by the lifetime, that is the okay, that is the total recombination current in the base. So, again if you put this Q dP, dP dx, what is that? It is this charge. So, this is the slope here of this line, okay, this charge divided by the emitter width, okay, by WE, which we let us call the emitter width WE. So, this is WE, this is WB, let us say this is WC, okay. So, again what do you get? Ni squared by Nd in the emitter okay, plus this component, okay. What is the total charge in the base? It is given by the area of this triangle, alright. So, what is the area of this triangle? Half base into altitude, okay. So, half, okay, sorry, here you have a W, I shall write here W E, okay. So, half, what is the base? W B into, again you have, there will be a charge, this altitude is what again? Okay, of course, you can write it in a better fashion by taking the exponential Vb by Vt minus 1 as common, okay. All right. Now the interesting thing is, so this is equal to 1 minus alpha f into If, Ib is equal to 1 minus alpha f into If. Now, if you take beta f is equal to Ic by Ib, okay, which is alpha f by 1 minus alpha f, okay, what do you get? Ic by Ib, okay. So, you have to divide this by this expression, alright. Now, obviously that exponential Vb by Vt minus 1, that gets cancelled out on both sides. So, what you are left with is, if you write it in this fashion, 1 by q dn ni squared by na, just write down the expression. You can do that for yourself, you get this expression. Now, this expression tells us a lot of things, okay. So, for beta to be high, okay, what are the conditions? What is dn tau n? That is ln squared, okay, that is the square of the diffusion length. So, for beta to be high, okay, WB must be, for high beta, WB must be very much less than ln, okay. Then Na must be very much less than NDE, and okay, the base width must be very much less than the diffusion length of carriers. That is quite understandable, because if the base width is quite large compared to the diffusion length, lot of recombination will take place, okay, the beta will be low. The acceptor impurity concentration in the base must be less than the donor concentration in the emitter, okay, because the base current is proportional to the if you look at the base current here, okay, it is inversely proportional to the donor concentration in the emitter, okay, whereas the emitter the collector current is inversely proportional to the acceptor concentration. So, all right. So, for a large beta, the emitter concentration must be much larger than the base concentration, and of course, the base width must be very much less than the emitter width, because that determines the slope, okay. So, if the emitter length is smaller, the slope is going to be higher and you have larger base current flowing in, okay. So, that also tells us, you know, we always sometimes hear this question that why we cannot, although it is an NPN transistor, why we cannot interchange the collector and emitter terminals, because the collector, okay, terminal, because the collector doping concentration is much less than the base doping concentration. Okay, this has to be made in order to, because you are applying a reverse bias across the, normally you operate you apply a reverse bias across the base collector junction, and also because of breakdown reasons and all, you have to make the collector doping much less, okay. And also so that the depletion region for the base collector junction goes on the collector side, not into the base side, all right. So that you do not have punch through condition, okay. So, for this reason collector doping concentration is much less than the base doping concentration. The collector length is also much larger compared to the okay. Of course, that is not a problem, okay. So, these are the conditions one must satisfy anyway. So, we shall go ahead. So, what we have is we have derived a relation for IS here. Now, suppose we have the other condition, that is VBC is equal to 0, okay. I just remove this. Suppose VBC is not equal to 0 and VBE is equal to 0. Okay. Then what is it going to be like? Okay. The situation, okay, if you calculate IE, okay, which is you can take the modulus, okay, because the signs will be different. Okay. This is given by, now you have VBC not equal to 0, VBE is equal to 0. So, these forward charges, okay, are missing. So, you have a situation like this, okay, and the emitter current is actually the current injected from the collector into the base, which flows into the emitter. Okay. So, it is just like the previous situation of VBE not equal to 0 and VBC is equal to 0, but you have just interchanged the emitter and the collector terminals. Okay. So, you have um, okay. Now, okay, so you have again q dn dn dx, and this one will give you a similar relation. What is dn dx? This is the same, okay, ni squared by na by wb exponential vbc by vt minus 1. Okay, because this voltage now is the base to collector voltage. All right. And what is this term? It is the same Is. So, we can write it as Is exponential okay. Now, all right. Now, if you look at these expressions now, alpha r IR is equal to Is exponential VBC by VT minus 1. Now, what is IR? If you look at the first figure here, on here, if we come back here, see IR is equal to ICS exponential VBC by VT minus 1. All right. Now, if you write it, if you replace IR there with ICS exponential VBC by VT minus 1, all right. And similarly, if you you have alpha f IF is equal to IS exponential VB by VT minus 1. So, if you again in that IF, if you replace IES exponential VB by VT minus 1, okay, what do you get? You will get alpha f IES will be equal to okay. So, basically what you have done is, you see, there is a relation between this alpha r and IES and ICS through this alpha r and alpha f. Okay. So, basically what it means that you can eliminate one of these 4 parameters, okay, all right, because you can write one of these parameters in terms of the other 3 and that can be eliminated, all right. So, basically you require 3 parameters. So, what we do is we use this parameter Is, okay, which is and we write the expressions in terms of alpha f, alpha r and Is, okay, and Is is related through this expression alpha r IR is equal to Is exponential VBC by VT minus 1, and similarly alpha f IF is equal to Is exponential VB by VT minus 1, okay, all right. So, that is the thing. Now, the situation where you have both the voltages applied, okay, that is the most common situation, okay, that is both the emitter voltage as well as the emitter base voltage as well as the base collector voltage is applied. Then what happens? What happens is the charge, okay, in the base or in the different regions is considered to be a superposition of the 2 individual cases, okay. So, you have this charge plus the reverse charge, okay, which is the sum is going to be something like this, okay. What happens to the slope here? The slope has decreased. So, what do you think about what should happen to the collector current? The collector current should decrease, isn't it? So, if you are forward biasing the collector base junction, okay, this end the charges are going to go up. So, the slope is going to reduce, okay, the collector current reduces. Also the total charge stored in the base is going to increase, okay, which is going to increase the base current. So, the beta is going to fall, all right. Okay. So, what we have done now is individually in the two cases, all right, you have calculated the collector current and the different currents. You can do that. IC is equal to Is exponential Vb by Vt minus 1, which is equal to alpha f If. Okay. Now, alpha r IR is equal to Is exponential Vbc by Vt minus 1. Okay. Now, if both the voltages are applied, the collector current is given by alpha f If minus IR. Okay. So, you can express that now. Okay. Alpha f If is Is exponential Vb by Vt minus 1, okay, and IR is Is by alpha r. IR is Is by alpha r exponential Vbc by Vt minus 1. Okay. All right. So, and similarly, because you can now express the different currents, okay, in terms of Is, alpha r and alpha f. Okay, these are now the three parameters. We are nowhere here do we have ICS and IAS occurring. We have Is, alpha r and alpha f. Okay, you can write the terminal currents, okay, when both the voltages are applied, okay, in terms of these three parameters. And what you get finally, I shall write that down finally. Also, you can express alpha in terms of beta, okay, because that is the more common, we use the common emitter configuration more commonly, okay, rather than the common base configuration. So, beta is a common emitter, it refers to the common emitter configuration, okay, current gain in the common emitter configuration. So, we can write beta in terms of alpha, and then the relations which we get, I shall write them down. Okay. This you can work out for yourself, I think. IC is equal to Is exponential this is just plain manipulation, okay. Basically you have to write IC is equal to alpha f If minus IR. So, alpha f If you know from the forward when the current is flowing in the forward direction, IR expression also you have calculated, and then you just write them in terms of Is and the two betas, beta f and beta r. And IB, okay, which is nothing but the difference of IE and IC, is given by plus okay, it looks very complicated, okay, but you can remember it very easily. Okay. If you look at these expressions, one can look at them as 3 current sources. Okay. One is given by this Is exponential Vb by Vt minus exponential Vbc by Vt, okay, which is occurring, okay, in these two, and the other two is Is by beta r exponential Vbc by Vt minus 1, and the third one is Is by beta f exponential Vb by Vt minus 1. Okay. So, you can write them in terms of this is the collector terminal, this is the emitter terminal, this is the base terminal. So, this is Is okay. So, what is the collector current is flowing down is this current source minus this current source, this is flowing this way. Okay. So, Is exponential Vb by Vt minus 1 minus Is by beta r exponential Vbc by Vt minus 1. What is emitter current? It is the sum of these two current sources. Okay. This is the same, this is this current source plus this. Okay. This is given by Is by beta f exponential Vbe by Vt minus 1, and the base current is given by the sum of these two current sources. Okay. And again all the currents are expressed in terms of the 3 parameters Is, beta f and beta r. All right. So, now you see, so this is the final Ebers-Moll model, okay, which is also available in SPICE. Okay. So, you have 3 current sources in which in terms of which you express the terminal currents. All right. So, you see that when the collector base voltage is say is almost equal to the base emitter voltage, okay, or it is forward biased, collector base junction. If you keep on forward biasing the collector base voltage, this current source value reduces. So, you have the current going down in saturation region. Okay. In saturation, what happens is both the junctions are forward bias, base emitter as well as base collector. So, this is the difference. Okay. The collector current is mainly made up of this component, which is the difference. Okay. If collector base junction is reverse biased, this component is almost 0, okay, because it is very small compared to this component. So, in fact, the current does not change much when you go on increasing the base collector voltage. Okay. All right. That is all right when you have a constant VBE, say almost the VBE is almost constant, and you go on changing the base collector voltage. So, the current will be almost a constant. All right. So, this gives us the relations between the terminal voltages and the currents, and this model is used, okay, in different circuit simulators. Okay. An interesting thing before we wind up, because we shall be coming to that again when in our circuits. I think it's the best time to discuss. Well, of course, if you plot the well known output characteristics of a transistor, for different base currents, we have this type of characteristics. Okay, that is all right. This is well known. So, this is for increasing IB. This is the collector current versus VCE. All right. So, what is happening when we come to this region? This is known as the saturation region. Okay, this is the active region. Okay, what happens when we go to the saturation region? VCE. What is VCE given by? VCE is equal to VBE, I should say okay. So, when VCE is going towards 0, almost towards 0, VBE is VBE and VBC are quite close to one another, all right. And so, you can see from this model here, when VBE and VBC are very close to one another, this current is almost going to go to 0. Okay. When VC is very large, it means VBC is negative, okay, because VBE as a forward voltage cannot be very large, all right. So, this is reverse biased, which means that the current becomes almost constant. Okay. The third point I want to make is, when VC is 0, what does it mean? VB is equal to VBC. So, if VB is equal to VBC here, what happens to this current source? This current source is 0. Is the collector current 0? Collector current is not 0, because individually VBE and VBC are not zeros. Okay. You have a current flowing here. Okay. So, IC is actually negative. There is a negative current flowing in collector, negative collector current flowing when VC is equal to 0, all right. And so, in fact, in order to make the collector current 0, VCE should be slightly positive, that is VBE must be slightly greater than VBC, okay, to compensate for this current. Okay. These two current sources must be the same in order to that collector current is 0. Okay. So, if you expand this region, okay, for a bipolar transistor, in fact, if I draw it here, this is IC, this is VCE, it is actually like this, okay, around the 0 point. Okay. This is called the offset voltage, okay, that is the collector emitter voltage at which IC is 0, okay, it is slightly positive, okay, and at VC is equal to 0, IC is slightly negative. Okay. We shall see that actually this transistor is actually operated in this point in when we discuss TTL circuits. Okay. There is a particular region, I wanted to introduce this here itself. Okay. So, we have seen the Ebers-Moll model of the bipolar transistor, which we shall be using in sometimes later on in the course. Okay. Okay. Thank you.